The ratio is 1/2. I hit times 1 divided by 2. The ratio of 1/2. In the last conversion, we hit 6.02. Remember the times 10 to the is second function e, 23rd power. Hit equal and see if we match with 4.88 times 10 to the 23rd power molecules of oxygen. We started with a mass. We went to the number of molecules. The 3 steps to divide, we ratio, we multiply, following the pathway on the stoichiometry roadmap. Let's try another. Read it with me. Example problem: how many liters of oxygen are produced by the decomposition, pattern of change there, decomposition, of 6.54 grams of potassium chlorate? Again, reading it through for the first time, I tend to just ignore the numbers, and I'm trying to pull out the recipe. I don't stand a chance of getting the stoichiometry problem right if I have an incorrect equation. I've got a decomposition pattern of potassium chlorate. I wouldn't think of predicting without pulling out our decomposition helpful hint page. There is a pattern of decomposition for chlorates. Take a look and see if you can find it. When metallic chlorates decompose, metallic chlorides and oxygen gas are released. Everywhere we said metal, you place the word potassium, and you'll literally hear the recipe for our equation. Potassium chlorate, when decomposed, gives potassium chloride and oxygen gas. There's the pattern of change from the decomposition. Potassium chlorate, when heated, decomposes to form potassium chloride and oxygen gas. Our skeleton is in place. Now let's balance. K's and Cl's are looking good. It's the O's that are off. If I have 2 on the right and 3 on the left, we'll turn them both into 6's and then go back to repair the KCLs. This stoichiometric ratio is a 2 to 2 to 3. Now let's go back and figure out what we're given and what we want to know. How many liters of oxygen? There's my target, a volume of oxygen. From the decomposition of 6.54 grams of that reactant, potassium chlorate. Given a mass, calculate a volume. Chart your course on the stoichiometry roadmap. The unit given is the mass of potassium chlorate. The unit we want is volume of oxygen. To move from the left all the way to the right are 3 steps. Step 1, we'll divide by molar mass. Step 2, we ratio, want over given. Step 3, we come down to the world of volume, where 22.4 liters, our molar volume, exchanges moles into liters. Step 1, Step 2, Step 3, let's set up our parentheses. Our given mass, 6.54 grams of KClO3. I like to get my parentheses ready so I can see my target. We want to land at liters of O2, the heart of our problem, the want over given ratio. In our first step following the roadmap, notice we need a molar mass. Turning grams into moles requires a formula weight for our reactant, potassium chlorate. 1 mole of potassium chlorate set over potassium weighs 39, 35.5 for the mass of a chlorine, and 16 times 3 for the 3 oxygens. That looks like 122.5 for the formula weight. A want over given ratio, we want to know the moles of oxygen. 3 is its coefficient. Remember, our target is the oxygen. 3 moles of oxygen are produced for every 2 moles of potassium chlorate. We want over given ratio. Step 1, we divided by molar mass to go to the mole. We set up a mole-mole dance, a want over given ratio, and now I'm standing here. Remember the desired unit? We want to know liters. Head down to find the volume of what we want. When we go down to find volume, we see that molar volume is our exchange. We know that 22.4 liters of oxygen is equivalent to 1 mole of oxygen. We divide, ratio, multiply, the 3 steps to stoichiometry. Hit it with me. Very important you become confident with your calculator skills. Start with the 6.54, the grams of given. Step 1 in the conversion says divide by that molar mass of 122.5. We'll multiply that by that ratio of 3 halves. That's typed in by saying times 3 over 2 times 22.4, the molar volume, and we find 1.79 liters of oxygen. Let's keep going. A next example. Assuming STP, how many liters of oxygen? And notice here, this is nice. They've given us the equation, so I don't have to work that part out. So I'll just tally what we're being asked to solve for. How many liters of oxygen gas are needed to produce 19.8 liters of sulfur trioxide in this balanced equation? Given a volume, calculate a volume. A volume-volume problem. Our journey would start at volume and have us go to volume. 3 steps to move all the way from the left to the right. A volume-volume problem. Let's get our parentheses ready. The given quantity of 19.8 liters of sulfur trioxide. There's our given. A step 1, step 2, step 3, where the heart of our problem is the mole-to-mole ratio. And we can see our target as liters of oxygen.